going to first properly define what an inertial system is, and we're going to see that this is not quite as easy as it may sound at first. There are really some circular reasons that you have to really try to avoid. And it's really important that you understand this, not just for general relativity, also for really all of your physics. The rules of physics are really not the same depending on what system you're in, and you have to therefore identify what system you're in. And that means you need some tools for this. Now, these things, for some reason, are hardly ever emphasized during your physics courses, so we really have to do this now, because if there's one thing that differentiates between special relativity and general relativity is the question, are you in an inertial system or not? If so, you can use special relativity regardless of what you are looking at. If you're not an inertial system, then you have to use general relativity regardless of what you are looking at. So it's really important to identify inertial systems. So that's object number one for today. The object number two then is, if you know that you are in a non-inertial system, how will the rules of physics change? And we're going to do this for Newtonian physics first. So forget about relativity in that point. Now, once we have seen how that works in Newtonian physics, then we're going to see how things change in relativity. And that will bring us directly to curved space-times. Now, given time, I will also make a small introduction on how you can describe a curved space-time mathematically. So today is not particularly math-heavy, but it is concept-heavy. You really have to understand what we're talking about. So really ask your questions if you feel that you've lost me, because today really is conceptually speaking, really the big step from what you've known to what we're going to do for the next couple of weeks. So let's start at the beginning. Can somebody identify an inertial system or define an inertial system? If not, don't worry, that's exactly what we're going to do today, but it is important that we have some starting points. So what, if you were asked, is an inertial system?
Maybe a system in which the first law of Newton.
A system in which Newton's first law holds. Okay, but that seems to imply that there are systems in which Newton's first law does not hold. Can you give an example?
Alright, if you like in a train that's accelerating, you like drop the ball and the ball goes like this.
Does it?
Yeah.
So, your suggestion would be something like this, yes? So you have your train. It's always trains in relativity, right?
Yes.
So you have your train, and then standing over here, and you're dropping a ball, and then you say there is some way that you can tell that you're not in an inertial system by watching the ball drop. What is that like?
Well, if you like in an inertial system, then the ball will drop like straight down without like moving to the left or right.
Okay.
But if you like in a non-inertial system, because of the acceleration, the ball should like either go left or right.
So you're saying something like this.
Well, technically speaking, an inertial system should the ball not drop at all.
Why would it?
Because once we have gravity, there's already, let's just say force. But then how do you differentiate between acceleration and gravity?
Okay, well, that is an extremely subtle and important point, but not one that we have to identify ourselves with, because the acceleration possibly of this train is going to be in the perpendicular direction to the dropping of the thing. So you cannot confuse these things.
Okay.
Agreed? But you are exactly right. We will see later on today that the acceleration, the non-inertial framiness, can be seen as gravity. Not in this particular case, because the acceleration is in this direction, whereas the dropping is in the perpendicular direction. So no chance of confusing these two, conflating these two. All right. So let's take Michaelis' idea that if this thing is accelerating with, say, acceleration A, then the ball would not drop straight down. Well, it will still drop straight down, right? It will still drop at this location. In fact, let me identify a couple of inertial coordinate systems. So let's say somebody on the train track put some coordinates there. They call this 1, here's 2, here's 3, exactly 4, 5, 6, etc. Here's one coordinate system. And let's also identify another coordinate system that we're going to draw on the train. Now, its 0 point, I randomly also put here. Let's call it a red coordinate system. Here's 1, here's 2, here's 3, there's 4, there's 5, and there's 6. Okay, now this red coordinate system is such that it is attached to the train. The train is accelerating, so that means the red coordinate system is moving in this direction. Now, you drop the ball, where will it end up? In either coordinate system, doesn't matter which.
Green, blue, and bigger green.
Yes. You would think that the ball will drop downwards towards number 3, yes, in the blue coordinate system. Not so much in the red coordinate system. And everybody understands why, right? I mean that the train is accelerating underneath the ball, so that means that if you happen to use your red coordinate system as your coordinate frame, you will see that the ball has gone from 3 to, well, whatever it is, 5 or 6 or so. Yes.
Ball falling down, but what is its initial velocity?
But it doesn't really, well, it matters for the number that comes out where it drops. It doesn't matter for the conclusion that it will not drop at 3. Agree? So of course, if I give it a little bit of initial velocity downwards,
No,
then it will
but I
probably
mean,
end up.
is it like in the acceleration?
Yes.
Is it going with the same speed at the beginning as?
Oh, that's what you mean.
Otherwise, it wouldn't fall down to 3.
So,
I just assume it starts off from blue 0. I mean, if
Okay,
the velocity is bigger than 0, it's going to drop from smaller 3 to blue 0.
let's say that at time t is 0, the ball has the exact same velocity and acceleration as the train did. Okay? That velocity could have been 0, could not have been 0. That doesn't really matter for the question. But we all see here that the ball will not drop at location, at the red location 3, yes, it will be 4, 5 or so. Okay. Now, that does mean that apparently from the red coordinate system, apply Newton's second law would have given you the wrong answer. Agree? Right? If you want to apply Newton's second law, what you do is, so forget about relativity for now, this is Newtonian physics. It will be something like this. And let's identify a couple of things here. This is all in x direction, yes? We'll also drop downward, that's not the direction that I'm interested in right now. So in the red coordinate system, and you would see the ball drop, it will not end up at 3, it will end at 4 or 5 or 6, depending on circumstances, right? Of the initial velocity and these sorts of things. But there was no force in x direction action on the ball, right? Yet you do see a drop at a different location than where it started out. And if you actually track how the ball is moving in x direction along the red coordinate frame, you will find that it is indeed accelerating along the red coordinate frame. That's interesting, because that means that this number is non-zero in the red coordinate frame, whereas this number is the force in x direction. So apparently Newton's second law is broken. It doesn't work. You don't have this problem in the blue coordinate frame force. So with this ax, I mean the acceleration of the ball with respect to the blue coordinate frame, it would just simply drop down, which is exactly what you would expect. If there's no force acting on the ball in x direction, then that means should have no acceleration, so therefore it should drop down exactly at location 3 where it started. So you see is something very important here, that you might have heard me say this before in other lectures maybe. But apparently there is a coordinate system here where Newton's second law holds, and there's one in which it does not. Now for some reason this is not emphasized in your course in Newtonian physics and or high school or these sorts of things. You cannot simply use Newtonian mechanics in any coordinate system. I can point out one here where it doesn't work. Now, here's going to be my definition, my working definition of an inertial system. An inertial system is for us going to be a coordinate system in which Newton's second law holds. So that in this particular example, that would be the blue coordinate system. Every coordinate system in which Newton's second law does not hold, the red one in my example, is going to be a non-inertial system. So that means that you have to be careful if you want to apply just your basic high school or first year Newtonian physics. Apparently, you cannot just use any coordinate system. Right? Your laws do not hold in all of them. Then all of a sudden it becomes really important to know which of these two you happen to be in. When you are dropping balls or throwing stuff or just doing any Newtonian physics exercise, you have to find out for yourself whether a particular given coordinate system is indeed inertial or not. If not, you run into a problem. You cannot use your loss of Newton. Now, how would you do this here? Based on our definition, our Newton's second law definition, how would you check whether a given coordinate system is inertial or not? You already gave it here, but I want to really stay on this point for just a little bit longer. It's so important. You might think, well, I know exactly which is my coordinate system, which is my inertial system, because I know it happens to be the train that's accelerating, right? If somebody steps on the gas or whatever you do with the train, and it starts to accelerate. And therefore, I can already identify that it must have been the blue system that was an inertial system, because the red one is accelerating, because I know where the forces were acting. Now, who can see a flaw in that reasoning? There's at least two that you can point out.
You could also argue that like the track is moving vertically.
Exactly. You could also say, well, maybe this thing was standing still, and it was just happened to be that this thing was moving backward, right? That would also have worked. In fact, Newton's third law tells you that it is equivalent. Because saying I step on the gas or whatever it is on a train, and therefore the train moves forward, that's, according to Newton's third law, would be equivalent to saying, no, the train is standing still, and you're just pushing your back. In fact, that is exactly what Newton's third law says. So apparently, this will not help you. And also, do you really want to identify inertial systems by looking for some train conductor stepping on gas? I mean, is that really, in this particular example, it might have worked. You just point out the window and look for a conductor somewhere or a machinist. But generally speaking, that would probably not work. In fact, let's make it a little bit more abstract. In this particular example, I've physically attached my coordinate systems, blue and red, to objects. One is the Earth, and the other one is the train. How about I drop a ball somewhere in deep space? No objects around. So in principle, you can define two coordinate systems. You can define a red coordinate system that is moving, it's hard to tell, but it's moving in space. But you can identify two coordinate systems, one of which is accelerating with respect to the other. Which one is the true accelerating one up in the air somewhere? So you go to deep space, you have the exact same situation, you drop a ball. You have a red coordinate system, you have a blue one. Which one is the inertial one?
The one in which the ball doesn't move at all.
Is it the one in which the ball does not move at all? Why would that be?
It's inertial because of Newton's first law.
I see. Okay. So we're converging towards Newton's first law again, right? Now, these are correct answers. But I really want to emphasize that this is a difficult issue. Yes, you have given the answer, but in order to really fully appreciate the answer, you have to fully appreciate the problem. If you didn't know about Newton's first law, and you only had Newton's second law to work with, you would have dropped a ball somewhere, and you would have seen it move backwards. Then in principle, there are multiple options, yes. Maybe in your coordinate system, the red one, it wasn't an inertial system, and therefore you saw it drop at different locations than 3. Or maybe red was an inertial system, and there is some unknown force of nature acting on the ball. Right? You can also have your ball drop, say, here or there, not because the red system is accelerating, but maybe because there is some unknown new force acting on the ball. Maybe a known force, maybe it's a charged ball, it happens to be a big magnet or something over here, or a big ball of neutrons or something, not neutrons, protons, something like that, yeah. Or maybe there's some new ball force, some fifth force that nobody knew about. So just looking at how balls will drop in a given coordinate system, and then applying Newton's second law is not enough. There might be some missing force that you didn't know about. So there really is a big issue here. Now, one final way that you might want to resolve this issue is as follows. If you say, well, Newton's second law, if an inertial system is defined as a system where Newton's second law holds, I'm just going to check whether there are deviations from Newton's second law. Now, suppose that you take your ball, don't have a ball here, let's suppose that I throw it. Okay. And I calculate where the ball would have dropped if Newton's second law was correct. That's a calculation I can do. It might be a difficult calculation analytically, but in principle you can do it. I can throw a pen, calculate where Newton's second law would have told me the thing would have landed, check whether it had landed over there. If it did, I can say, aha, there we go. Apparently I'm in an inertial system because Newton's second law holds. You don't make sure that you don't make any mistakes in your reasoning, but this is something you can do. You might also say, if then the thing did not drop where I expected it to drop, then apparently I'm not in an inertial system because my Newton's second law did not hold anymore. That sounds like a way that you could resolve this. I can see you shake your head, so
I mean,
tell what the
you
force
would
is.
already need to know what the force is to
There we
use
go.
the law.
Exactly. So
So
if I
maybe there is
would-
no force at all, but you're accelerating, you'll never know.
I know, that's exactly the point. Right? Here's the issue with this particular proposal for a test. If I were to throw the pen, and I were to calculate where it would have landed given that Newton's second law is correct, I should have already known what the force is with which I threw it. I should have known this number in advance, right? Now, how do I know that number? Well, you measure it, but how do you measure it? Well, you measure it by measuring how fast it is accelerating and then calculating back what the force was. But then you end up with circular reasoning, because you can only use this law if you know that you're in an inertial system. In order to do the test whether I am in an inertial system, I need to know my F, but I can only find my F if I knew that it was in an inertial system. So you end up in circular reasoning. So all of this is just me convincing you that Newton's second law by itself is not enough to tell you whether you are in an inertial system. Every test that you want to do just based on Newton's second law requires you to have already known beforehand what F was, and you could only identify F by using Newton's second law. That's circular reasoning. And there's no way around this. There's absolutely no way that you can define a test just based on Newton's second law that will tell you whether you are in an inertial system. You will always, somewhere down the line, end up with this circular reasoning. I really challenge you to give me a test where this does not occur. You could, for instance, say, well, but what if I don't throw a ball, I take a proton and I put it in a known electric field. So I know exactly what the force was without me having to throw it. Okay, but then you should have known beforehand what the charge was of your particle, agreed? And how would you have found the charge of your particle? By letting it go through an electric field. Circular reasoning.
What if you know that it's a proton?
How would you know? Because the proton is defined by its mass and by its charge. And those two numbers you can only identify by using the second law.
What if you figure out it's a proton in an inertial frame and then move it to a new unknown frame?
But then,
Still a proton.
I agree. Suppose that you would have gone to an inertial frame first, found out that it was a proton, then went back to your other frame, and then would have known it's a proton, and then you could do this test. But then you had already identified an inertial system to begin with, and then you wouldn't have the problem to begin with. Do you agree? Somewhere in your reasoning, you needed an inertial frame, and that was exactly what you did not know before. So there is always a circular reasoning here. Now, these gentlemen already gave the solution to this. You might have heard me say this in other courses or so. The only way to get out of this circular reasoning is to have some external law that tells you, without making use of Newton's second law, whether a given frame, coordinate frame, is an inertial frame. That's what Newton's first law does for you. Newton's first law is not just a special case of Newton's second law. Unfortunately, this is sometimes the way that you read it in books. That you say, well, you know what, if you put F to 0, then you have a zero acceleration, so therefore constant velocity. Oh, well, there's Newton's first law. Newton's first law, only a special case of Newton's second law. No, that's not true. Because, again, you're using Newton's second law, so therefore you already knew that you were in an inertial frame. So, Newton's first law is a trick. It tells you how to do this. So, you tell me. I mean, I've given you the hint that Newton's first law will tell you whether you are in an inertial frame. How do you do this? How do you avoid the circular reasoning by using Newton's first law?
Just have no force. You know you have no force.
Yes,
You know nothing's going to happen.
exactly. Of course. The problem with the circular reasoning here is that you should know the F beforehand. What if you just make a situation where you know that there are no forces? How to do that in practice? That's a question that we're going to solve during the tutorial. But suppose that you find yourself in a situation where you have made sure that there are no forces acting on the particle. So you don't have any trouble with identifying how much force there was. You made it to be zero.
How can you know that? Because you can have an acceleration that completely cancels out the force.
That's a very good question. And there is a solution, which is exactly tutorial exercise. Conceptual tutorial exercise. Okay? So I'm only sort of giving you half the answer here. But maybe during the course of this main lecture you already see where I'm going to get it. But do you see that if you have made sure that a particle really does not feel a force, and it still accelerates, you don't have any trouble saying, well, I got the zero force for circular reasoning because you got it from Newton. You can get it externally, yes? And then you end up with the situation, okay, no force, yet acceleration. In other words, you're breaking Newton's first law, no inertia. It's a very important point here. Newton's second law gives you circular reasoning if you want to know whether you are in an inertial frame. So you need an external rule. What is the external rule? Make sure that there are no forces. How? Good question. See tutorial. Make sure that you have no forces. If you have no forces, yet you have an acceleration, in other words, when you break Newton's first law, then you know definitely that you are in a red system and not in a blue system. Yes?
So is the Newton's first law explanation a sufficient condition for an inertial frame?
Yes.
Or do you also need Newton's second law to hold
No.
that redundant?
No, that's then redundant.
Okay.
Well, I mean, Newton's second law is not redundant because it can give you something Newton's first law cannot give you, namely how things exactly will accelerate.
Yes, but in defining an inertial frame,
You only need Newton's first law.
Okay.
And that puts Newton's first law on a ridiculously high and important pedestal in physics. It's not just, again, a special case of Newton's second law. It isn't. It's really an external law, something that tells, a law that tells you something that Newton's second law could not. It defines inertial frames. And Newton, the scientist, knew about this. It's no coincidence that he put this law before the other two, okay? Before you can apply the second and third law, you need to have checked whether you're in an inertial frame. So the first thing that you do is use Newton's first law to do that check. Only once the check has been passed, then you apply Newton's second and third law. Otherwise, you can run into these sorts of issues. Now, that defines an inertial frame. Any coordinate frame in which Newton's first law does not hold is a non-inertial frame. And that's a completely sufficient criterion.
Wait, just 5 minutes ago you said when the second law does not hold, it's a non-inertial system. Now you said it's a
Yes,
first.
and then I said it was a working definition.
Okay, yeah.
And then the reasoning that I followed was that by itself leads to circular reasoning. So you need an external one. The external one is Newton's first law, and Ali's question was, is that insufficient? Do you then still need the second law? The answer is no. Once you have the first law as a check for inertial systems, then you're done. You still need the second law to calculate how things will then accelerate. Okay? So, that will define our inertial system. Now, going back to relativity for a second, now we know that Newton's first law checks whether you're in an inertial system. We also know that Newton's first law isn't just a check whether you can use Newtonian mechanics. It's also exactly the check that tells you whether you are allowed to use special relativity or not. If you find yourself in a coordinate system where Newton's first law is upheld, use special relativity, regardless of what you're looking at, whether that thing is accelerating. If you are in a system where you find that Newton's law is broken, you are in a non-inertial system, and you have no choice but to use general relativity. So, big pedestal, Newton's first law tells you, it's the big check that tells you whether you should use special or general relativity. Okay? Any questions on this? Because now comes the fun. What happens if you go to a non-inertial system? Yes? Are you waiting with anticipation? Well, you can already sort of see it happen here. Let's go to a non-inertial system. The red one here. Okay? Apparently, things accelerate even though there was no force acting on them. Right? So what do people do? They say, well, you know what, let's pretend that there is a force. Just to explain, quote unquote, the acceleration. That has a name. Yes, that's exactly right. If you go to a non-inertial system, things will spontaneously accelerate even if you cannot identify forces acting on them. So people just pretend that there are forces acting on them. They call those fictitious forces. You understand the word fictitious here, yes? Because it's not like electromagnetism or the strong nuclear force or spring force or muscles or whatever. It's really just you having made the bad decision of trying to explain your stuff from a non-inertial system. In fact, that gives you another criterion to define whether you are in an inertial system or not. If you find that things are accelerating, and you know what? You go to some other coordinate system and you find one where that force has gone, then apparently that thing wasn't a fictitious force. Right? If you're in a non-inertial system, things accelerate, you pretend you wouldn't know any better than there's a force acting on it because it's a fictitious force. If you can find a coordinate system where that fictitious force has gone, then apparently the original coordinate system in which you were was a coordinate system. There was an inertial system. Yeah, parse that sentence for a moment.
So you do the same experiment in 2 frames.
Well, possibly 1 million of them, right? Because you have to randomly look for one where that force has completely gone.
But you do the same thing
Yes.
every time.
Yes.
You can see
It's still Newton's first law.
Okay.
So you apply Newton's first law to all systems and something to find the right one. So what is the big point here? The big point here is non-inertial system means fictitious forces. That means, by the way, that's good news for people who really, really like Newton's second law, that you can still use the formula. It's just, aside from putting in your actual physical forces, like electromagnetism and all this stuff, you have to, by hand, put in this fictitious force to compensate for the fact that you have an extra acceleration due to not being in an inertial system. Does anyone happen to have an example of a fictitious force?
Dark energy?
Dark energy. I'm going to
Probably
leave that one
not,
out.
but-
No, I'm going to leave that one out. It is fictitious in semantically speaking, it is fictitious in many ways. But
Yeah, I know it's probably not related, but that's the first thing that came to mind.
I understand, but this it's much more close to one, much less exotic.
Yeah,
Centrifugal
gravity.
force.
Oh. And here's centrifugal force. Well, that is indeed true. In fact, let's derive the centrifugal force, knowing this stuff about inertial and non-inertial systems. By the way, here's another one, right? I mean, if you were to look at this ball and describe how it would move in the red coordinate system, we already concluded, well, you see it accelerate backwards. You know immediately what its force is, right? This fictitious force that you can pretend acted on the ball. Because you say, oh, look, the thing is being pulled backwards to, what's the little f by, this fictitious force. Can you tell me what the formula would be?
Minus MAF.
First of all, minus. How much is it accelerating backward in the red frame? Well, as much as the train is moving forward, yes? So it's minus AX. Yeah, and there should be an M in there because an acceleration by itself doesn't make a force. You have to multiply with M. So, here's a fictitious force. In fact, this is a fictitious force that you feel, right? Your airplane, when it starts speeding along the runway before it moves up, you'll be pressing your chair. That's this force. It's your body trying to say location 3, whereas your red coordinate system, your plane, is accelerating forward. And you experience as if you're being pushed against your chair. It's really your chair pushing against you. So in that sense, a fictitious force is not really fictitious in that sense because it is actually a measurable effect. You actually do feel your chair being pressed in your back. So here's an example. Another example that I heard somebody mutter is a centrifugal force. Now, we all know the centrifugal force, at the very least from experience. If you're standing on something that is spinning around, it doesn't need to accelerate in its spinning, just a constant velocity, spinning around. You feel that you're being pushed outward, right? You take your little brother and you're swinging by his arm or something like that, and you let go of him and he just flies off. It's also the same thing that if you would, take your bucket with water and you put it on a little rope and you swing it around fast enough, the water will not drop down because something is pushing the water against the bottom of the bucket. Let's draw this situation now. What I have here is indeed, I'm going to make this a spinning disk. So this is the overhead view of the spinning disk. It could be a merry-go-round or something like that. It spins with some angular, let's make it a constant angular velocity. You don't have to, for exercise, it's a little bit easier to make it a constant one. Constant angular velocity, this thing is spinning around. Right? Now, let's define the coordinate system. Let's suppose that we have already checked beforehand, by using our Newton's first law trick, that this blue coordinate system, this one here, is an inertial system. Right? Now, we can go into all kinds of pragmatic issues because the merry-go-round is probably built on Earth and the Earth is maybe not an inertial system. Let's forget about those issues. We found an inertial system with the merry-go-round. Yes?
I mean, this might be a bit of a stupid question, but if you put something into the middle of the merry-go-round, Newton's first law is still going to hold.
In the middle.
Well, it's not going to hold for rotation, I suppose.
Well, first of all, there is an acceleration. I hope everybody sees this.
Yeah, no, I just didn't think that through. So good.
But just to make this small point, there is an acceleration, not in the velocity with which the merry-go-round is spinning, but in its direction. Right? Change the direction also is an acceleration. Now, again, suppose that we have checked beforehand that this xy, this blue coordinate system, is indeed an inertial system. Now, let's also identify a red coordinate system. And the red coordinate system spins along with the merry-go-round. And let's suppose that t is 0, two x-axes were lined up. You don't have to make it as difficult as you want, but let's for simplicity say that at t is 0, the red one was laid on top of the blue one. Now, let's look at what masses will do. But let's look at how a particular mass will move as seen from each of the two coordinate frames separately. Now let's take a mass here. There's a mass. Let's call this point P. And suppose that it was traveling along with the rotating disk, and at this point was let go. This is you taking your little brother, swinging him around to let go. Yes, at some point. The letting go part happens here. Let's look at how this mass will move as seen from the blue coordinate frame. How will it move? You know it's an inertia frame. I see people do this.
Or bump on the way to the exit.
So, like this, yes? Well, that's exactly what Newton's laws tell you. You know that the blue system is an inertia frame, so you know that Newton's laws hold in that frame. So you know that if you let it go and there's no other forces acting on the thing, right? It's your little brother just freely flying through space. It will move in this direction. At some point, I'm sure it will end up here. No problems there, right? In fact, we can even tell how much distance it will have traveled in a particular time dt. So how much distance is there between P and Q? No relativity needed. Go back to when you were 15 and 14 and had your first high school physics. Let's say that when you let go of him, he had velocity v.
I mean, VT,
Or delta dt or delta t. There's a difference.
yeah.
Okay. So, of course, this is the distance. All right. So no problems here, right? Everybody understands why this works. Now, we're now going to view the same thing from the red coordinate system. Now, before we do the mathematics, note something interesting here. In the red coordinate system, at t is 0, it started at this point. We should give things names, I suppose. Let's say that the merry-go-round has a radius of capital R. Right? Or, in case of your brother and swinging around, this is the length of the arm. So, at t is 0, when the two axes were still lined up, the mass started at x prime is R. Now, when it crosses here at point Q, well, apparently, in the red coordinate system, the mass is not at distance x prime is R anymore. It's moved a little bit outward. It's moved this amount outward. Let's call it dx prime. The amount of xness that has moved outward as seen from the red coordinate frame. So already, without having done the mathematics, you can tell that in the red coordinate frame, apparently this mass is being flung along the x prime axis outward. Right? You would have expected the mass to have ended up here, but it actually does end up here. So there's a little bit of difference in there, and that amount of difference is what you would experience if you were to measure the motion of the mass as seen from the red coordinate frame. This is what you feel, yes? This is what you feel when you are on this really speedy going merry-go-round. You feel as if you're being radially pushed outwards. You're not. You're really just in your blue coordinate frame, you're just happily following Newton's first law. It's just you happen to have chosen the wrong coordinate system to describe your motion of your mass in. Now, we don't have a force yet, but we can already sort of see where the force is. It gives the impression in the red coordinate frame as if something is pushing you along the x prime axis outward. And that force must be such that apparently in the time dt, you have been pushed dx prime outward. Now, this is the fictitious force. There is no force pushing you outwards. It's just your really Newton's first law inertia from your blue frame that you happen to have accidentally been seen from a red frame. But we can derive a formula for this easily, right? How about we do the following? How about if we look at this picture very carefully in a moment, we get an expression for dx prime. You can already tell it's probably going to have something to do with dt prime. Or more than dt. Difference between dt prime and dt Newton in this. You can already tell that this will have something to do with this because if dt had been the bigger number, it would have been here, it would have been a bigger dx prime, yes? So, this is going to give you something, exactly what we will see in a moment. It's going to be something as a function of dt prime. Maybe a square, maybe a logarithm, maybe a sine, what have you. But it is going to be a function of dt. We can turn this into an acceleration. An acceleration along the x prime axis. How? Take its derivative twice. But if you know, so we will end up in a moment with an acceleration along the x prime axis. And then we turn it into a fictitious force. This acceleration that feels as if something is pulling on you outwards. Now, how do you get that quote-unquote force? Just stick a mass in front of it, right? So do you know from your high school physics what the answer is, by the way? Dutch people probably think of a Benos right now or something like that.
For the dx?
Sorry?
For the dx?
No, for the total force. For the non-Dutch people, students in high school in physics get this little booklet that has formulas for chemistry and physics, and people who don't understand physics look at the booklet, look at the exercise, what numbers they were given, look at the formula contains 2 out of the 3, and then use that number and just plug in numbers, and then hope for the best. Okay. Let's derive this first, so that you'll recognize it when we have it.
The centrifugal force.
Sorry?
So like deriving the centrifugal force. Now.
Yes. draw a little triangle here.
It's not necessarily a rectangle.
That's this triangle. I'm gonna draw here. And this side of that triangle is VDT. Agreed? This is the number that you want to know, the x prime. Still clear on this? In fact, let's make life a little bit more easy. Let's call the angle that it has traversed the disk in this amount of time dt. Let's call it alpha. And the alpha is here as well. That's this alpha here. Okay. That immediately gives me an expression for the x prime. I'm waiting for somebody to make a comment, but in the meantime, I'll happily continue along.
Yeah, why is that necessarily a right angle?
That is exactly the question. Let me write it down first, what we get would be x prime, and that will answer your question. But that's exactly the question I was waiting for.
Is Thales's theorem?
What does Thales's theorem say?
If you IF only works for full circles, right? So well, usually it's like if you draw a circle and have 2 points, like have a half circle and the 2 points are part of a triangle, any point that is on the line of the circle is going to give you a rectangular triangle. Rectangular triangle, yeah, triangle containing a 90-degree angle.
I missed the first part of the theorem.
If you have 2 points and a half circle, any point on that half circle will give you a right angle.
I see.
I see, okay.
I think.
That works.
So maybe.
Yeah, but you know what? In
I
real
mean-
life, this will be a curve, yes? And I write it as if it's just a straight line. In real life, this would have been a little bit curvy, if you look at the picture. So if you really look at it closely, I wasn't even allowed to draw a triangle at all, let alone the right angle. But what if we make our dt very small? Small amount of dt. Let's be honest here. I'm not smuggling. I mean, the reason I'm going to take a small dt is not because I really, really want this expression to come out. It's because once I would have gotten my dx in a moment, I would have taken my derivative twice, agreed? Now, if there's one thing that the derivative with respect to time does, is tell you, let's take the limit of dt to 0. This is what derivative taking is. So, knowing already in advance that I'm going to take my dx prime in a moment, I'm going to take 2 derivatives with respect to time. So one of them would have already done the trick, but we're going to take 2 even. Derivative taking, by definition, means make your dt prime, your dt very small. Well, if I'm going to do that anyway, might as well start with a really small triangle here. And then by extremely good approximation, this will become a triangle with a rectangular angle in there, 90-degree angle. So I'm really already sort of half taking derivative here. By already taking my dt to be very close to 0. And that same, so you get this expression, agreed? Okay. By the same token, that means that this is about alpha. The smallness of dt tells you that the angle could not have been very big. Let's go back to the blasphemous whiteboard over there that says that the cosine of theta is about theta. I don't know who wrote that down. I hope it's not a physicist, okay? Or a mathematician. Well, biologists, that's fine. Right? No, I mean, they have different skills. The sine of a small angle is about the same as the angle itself. And since we have a very small angle here, because we have only given dt an infinitely small amount of time, this is true. So that's in the limit that dt is ridiculously small, as you would have in the derivative yet to be taken, this is true. Now, let's mark this result for a second. Let's draw another triangle. So let's box this, we're going to use it in a second. Here's another triangle. DDT, it's this one. Forget about that there happens to be some curve in there. Let's look at the big one. We don't even have to worry about whether this is a 90-degree angle. It really is, okay? Even for the non-small dt. What is this distance? That's r. What if we could take this new triangle, get an expression for alpha from that one as well? So get an alpha from this one, plug it in here, and then we will have the x prime in terms of all the other stuff, yes? So, you tell me, how do I write alpha in terms of r and v's and dt's? Like cosine. So I'm not going to use the hypotenuse, so this will give me a tangent. Tangent alpha here equals
VDT over R.
VDT over R. By the way, I'm a little bit sloppy in my notation. Here's infinitely small dt, let's do it here as well. Over R. In order to get this, I never needed to say that dt was a very small number, or equivalently that alpha was a very small number. But I am taking alpha to be a very small number. I did that before, might as well do it again. Also not written on the blasphemous board, the tangent of alpha is also equal to alpha when it is very small. Should be no surprise to you. Tangent is the sine divided by cosine. The sine of alpha goes to alpha. The cosine for small alpha goes to 1. There you go. And in the limit of the derivative yet to be taken is exactly equal. Let's combine effects. Take this one, take that one. I will get dx prime vdt equals vdt over r. Happily moving onward, highbrow mathematics here. I get v squared dt squared over r. Here we go. I have my expression for dx squared, dx prime, the one that I was looking for. The amount that the red coordinate frame sees the mass moved outward radially. That I've now found in terms of the radius and in terms of the velocity with which the thing was moving. So my object was to find the acceleration, and from that, its fictitious force. So how do we get acceleration from my dx prime? Yeah, you would think so, yes? Differentiate twice with respect to t or something like that? But remember, we are already in the limit where dt is very small, and then differentiation is literally just dividing twice by dt.
Isn't it just divide by time?
Yes?
So you just divide both sides by VT squared.
So my a along its x direction. So remember, I've already, in my derivative taking, what you typically do is that you take your dt to be very small. I already did that in some steps prior. And that means that all of a sudden my derivative taking is literally has become the same as dividing twice by dt. So I now know, in the red coordinate frame, how much you see the mass being accelerated radially outwards. Final step. Let's turn it into a fictitious force. Let's pretend that there was a force pulling the particle outwards. What would that force be? F fictitious. Easy question. You have your acceleration, you need to turn it into a force. You just put your mass in front. Back to the Dutch people, be honest. This is centrifugal force. The thing that pulls you outwards. So here's a beautiful demonstration of that the centrifugal force in the true Newtonian sense of the word is not really a force at all. It's an acceleration you experience because you look at this mass from a non-inertial system. There you go. Any questions on this? Because before we go into break, I want to point out a couple of things that we're going to use after. Yes?
divided it by dt squared, but
Yes.
I didn't understand.
Well, if I have my distance and I want to turn it to the acceleration, usually I would take two derivatives. And the derivative, because we're already in the limit of dt being very small, the derivative, two derivatives is just dividing twice by dt. That's what I do. So we have two examples of a fictitious force here. This one, because you happen to choose a coordinate system that was rotating itself, not an inertial system. We have another one here. I don't know if this one has a particular name. Let's call it carry your back force or something like that. Also the result of you going into a system that is not an inertial system. And there's one very obvious similarity between these two forces and all fictitious forces that you care to calculate in this particular way. They have a mass, absolutely. Now, do all forces have a mass in it? Can you give me a force, a true non-fictitious force? Sorry? The Coulomb force. The Coulomb force is proportional to the charge of the particle and the distance from whatever other charge is pulling on it. No mass. Give me another force. Sorry? But it's not a force, though.
Well, you got the weak and the
Yeah.
strong nuclear forces.
Yes. Now, it so happens that the strong and weak nuclear forces are called forces, but they cannot be written down in a Newtonian F equals something something equation because they're highly quantum mechanical and there's no classical analog of this. So it's still called force, but they should have called it interaction or something like that.
Okay, so from the four forces that we have, one is gravity, which is not a force, and the other three are quantum mechanical and cannot be defined as a
The
force.
two at least are quantum mechanical.
Okay.
The other one is the electromagnetic one is classical, but you could say Lorentz force, right? Magnetic particle, or magnetic particles. You know what I mean? Magnets would feel in, or moving charges would feel in a magnetic field. It goes with V, it goes with the B, and it goes with Q. No M's. But by sheer definition of a fictitious force, where you first look how the thing would move in the blue system, in an inertial system, then calculate how the thing looks in a red system, and a non-inertial system, you end up with an acceleration. In order to make it a force, quote-unquote force, you have no choice but to multiply with m. So, all fictitious forces are always proportional to the mass of the particle. Yeah? It's not just these two examples. I hope that you see the general strategy how you get a fictitious force to begin with.
Yeah, because the fictitious thing is the acceleration in the first place, not the
Yes.
force itself.
Exactly. Every time that you start with a blue frame, an inertial frame, you see how things move. Then do the same calculation in a red frame. You always only end up with an acceleration. To make it a force, have to multiply it by m. In other words, fictitious forces are always proportional to the mass of the particle. Now, if you've understood that point, still no general relativity here, just Newtonian physics. That automatically means, so let me write down the conclusions, fictitious forces are always, not by coincidence, by construction, by definition of the thing, are always proportional. I might have said perpendicular just a second. I meant no, I didn't. Good. If I did, I meant proportional. It was somebody in yes. Dear sir, I like your lecture. Are always proportional to mass. The mass of the particle on which it is pulling. Okay. No beating around the bush, this is what will happen. That has an immediate consequence. As I've said that, we can go to break. Namely, if you so choose that you're going to describe how a mass is moving, Newtonian, no relativity, just how a mass is moving in some coordinate system, it happens to be a non-inertial system, a red system, then you know that you will find some fictitious force. You will know that it's going to be proportional to m. And, let's see if you can parse that last step, that automatically means that all masses, as seen from the red coordinate system, will move in exactly the same way. Parse that last part. See if you can understand why that is.
Wait, but why is this the case for particles with mass? I mean, the formulas are the same if you use electrical force, right? Then and you just substitute mass for charge.
Approximately question. Can you repeat one more time?
Okay. I'm not sure if I can. Well, if you use another force like electromagnetism,
At what point?
well, you have F is MLA, M times A, right? Just substitute M for electrical force.
Sure.
Then the whole thing that you just explained still works the same way, right?
No, it doesn't. At the moment that I would have, well, first of all, note that I never used any forces to begin with. Right? This mass here that was moving upwards was not under influence of any force. It was just freely moving, cruising through space with constant velocity. That was all that I needed to end up with this equation here.
Right, because if there was charges involved, then they would track.
So why couldn't it just be in a huge magnetic field, for example? Wouldn't that not be different?
So you're saying, let's take this thing, let's put a huge magnetic field on top. And then?
Well, then you always have a force acting because it's a magnetic field.
Yes.
So could you also create a non-inertial frame just by using, for example, magnetic field? Because everything you put in there is going to have, like everything that is charged in that you put in there is going to move. And you also know the way of checking what the absolute zero magnetic strength is.
Yes. There is a point here. In my derivation here, this one as well as that one, I assumed that there was no, I suppose, fictitious force, no real other forces acting on the particle. Yes. So by definition, by premise, I started with a situation where there is no magnetic field or what have you. Then I end up with this. We agree on this, yes? Okay. Now I can still add a magnetic field or whatever to the whole system, make this a charged particle. It will move according to this magnetic field, and yet on top of it, it would also still feel this way. You
Yeah.
would just be adding extra forces. So you would still not get around the fact that there is a fictitious force. It's just a fictitious force plus something else. Yes.
Going back to what you said, that all masses will be.
Yes. That is the step that we have to fill right now.
Oh, yeah.
Okay. Well, or do you have an answer?
No, I just wanted to.
Okay, well, that's exactly what we're going to do, and then we're going to have to go to a break, okay? So, one more time. We have seen now fictitious forces. Yes, good questions. I'm deliberately now leaving out other forces, okay? So, it's really just Newton's first law operating and seen from a red corner frame gives you something that resembles a force. That force is always proportional to mass, by construction. And then that's this statement. Then my next statement was, and that means that all these masses, in absence of other forces, they could take their content into account, in absence of other real forces, all these masses will have exactly the same acceleration, the same way of moving. How can you tell? From this statement,
They're
that
in
that's
the frame. All masses in the frame.
Yes. Yes. But how would you find that? It's almost right. It's hidden in plain sight. That this statement that fictitious forces always come proportional to mass is equivalent to saying, therefore, all masses under this fictitious force will travel in the same way. How do you calculate how things travel in Newtonian physics? How does one do that?
It's divided by
You take Newton's second law, agree? And, well, in absence of any other forces, in a red corner frame, this is a fictitious force. Could be that one, could be that one. Yeah, but this one is always proportional to m, right? Mass cancel out. So here's yet another way, Ali. This is what I was promising when you were asking, but how do you check whether there are no real other forces around? Can you tell how in this particular case?
How do you check if they're?
Yeah, you were asking me before. I said, well, it's supposed that if you want to take your Newton's first law test, you make sure that there's no real forces acting on them.
Right.
And then you ask me, but how do you know whether there are no real forces acting on them? Can you tell by
check
this
how they
thing?
move, and if they move in the same way, then you know it's a fictitious force.
How about you take multiple particles with completely different properties, different charges, different magnetic properties. And all of them have exactly, because the m is dropping out, have exactly the same acceleration, and therefore apparently that force you were feeling could not have been a real force, must have been a fictitious force. So that really is already the answer to one of the exercises from the tutorial, so forget what I said, okay? But conclusion here is, non-inertial frames introduce fictitious forces, they're always proportional to mass, and as a result of that, everything under a fictitious force will have exactly the same acceleration, and if you will, that means follow the same path, regardless of what that object is. Charges, magnets, people, your little brother that you're flinging around, all of them will move the same way. Okay.
But if they all of them have different mass, will they have like the exact same acceleration?
Yes, because the m drops out, yes. The m that you put in yourself to make your acceleration into a force drops out against the m that was already in Newton's second law. So your a that you will get out is whatever it is going to be, but it's not going to be mass dependent.
So everything. Fictitious force are like the exact same acceleration.
Yes. So maybe that's good. That's maybe a good way to summarize this. Under fictitious force, all masses will have the same acceleration. That's a very good way of getting to this conclusion. Okay, good. We now know what happens in non-inertial systems in Newtonian physics. Let's have a bit. Let's see what happens in relativity.
I think it's really basically a really cool this is the time. This is a just about
Okay.
see what
Okay.
stick around for more. Let's see what happens to the
Yeah. Just leave it there.
I was going to ask, do you know of any other
Okay, people. We have succeeded in, well, let's say 75% of our goal for today. The only thing that we still have to do is see how things work when you go to general relativity. Let's say, you know that this is the object of this whole series, right? It was actually in the name. 19,006.
I was talking about something else.
Okay. What's talking about general relativity? Oh no! Well, she meant something else, fortunately. Okay. I was just about to see that giveaway was the name of the course. At some point, this topic would come up. So, 75% I think of the object for today has been reached. We still have to find out how things will, what will happen in non-inertial systems when you go to relativity. Now you already know the general relativity will come into play. What does that mean? That's the whole idea. And in order to do that, there's another conceptual thing. Park this for a moment. Yes, we're going to return to this in a moment. Leave this for now. Let's start with a different story. We are going to talk about something that is called the equivalence principle. In fact, it already came up when we had this sort of open discussion moment when we started our lecture series. And some people brought up the equivalence principle. I think it was Giovanni. And he had a couple of different interpretations of that thing. And that is because the equivalence principle does come with different interpretations. And they're very closely related, not exactly the same. So it's almost a matter of taste what you consider to be the equivalence principle. For our particular purposes, I'm going to adopt for the equivalence principle the following statement. Something you probably already know from experiments, namely inertial mass is the same as gravitational mass. Again, many different ways to build up the equivalence principle. My starting point is going to be the following. That there's really two meanings of the word mass in physics. There's even more, let's put those aside. One of them is something that I will call MI for now. It's called the inertial mass. And by inertial mass we mean the tendency of objects not to be accelerated. Inertial mass. So the bigger an object's inertial mass, the more it resists itself against being accelerated. The tendency to resist acceleration. That's a nice way of putting it. Do you have to know a formula for this? Something that tells you that contains the inertial mass, what exactly this particular physical means. Well, that would be Newton's second law, right? I mean, so let's put the I there. That's really what it is. It tells you that if the more mass something has, then pushing against it with the same force will produce less acceleration. So it's literally exactly in formula what is written here in words. So that's something that we would call the inertial mass. Now, you also have something which you call the gravitational mass. Now, the gravitational mass is, well, the tendency of an object to be pulled towards another object by the force of gravity. It's what charge would be in electromagnetism. It's the charge of gravity. So, it's called the tendency again, for lack of a better word. The tendency to be attracted, by attracted I mean gravitationally, to other masses. And you know a formula for this particular mass as well?
Big G.
Big G, okay, there you go.
Is one and two. Is it a Swarovski? Is it a
This is big G, 6.7 10 to the power minus 11.
right?
We can also write maybe small g times m or something like that. Right? And this is going to be the gravitational mass, where g according to the Blasphemous Word is about 10 shows of the Earth. Now let's be a little bit more general. Let's stick to real Newtonian physics, even outside of the near proximity to Earth. Then yes. So the mass that's being attracted times the mass that does the attracting divided by their distance squared. There you go. Now we are extremely used to using these two masses interchangeably. When I tell you what my mass is, I have to report to you that it's now 84 kilos. Diet works. I'm really telling you two things. I'm telling you something how strongly I'm pulled towards the Earth, and at the same time, I'm also telling you how difficult it is to push me aside when you start pushing against me. So it's really two statements I'm giving you. Okay. That these two numbers are given by the exact same actual value, in my case 84 in some unit system, is a complete mystery to this day. We have two completely different things that apparently are given by the same number. Very strange indeed. Now, sometimes people think, oh, but how difficult it is to push this guy aside has something to do with his gravity, because the gravity is putting him on the ground, so the more he's being pulled on the ground, the more difficult it is to push aside. No. Take the Earth away, hang me in space, try to push me aside then. Okay? Still difficulty, no gravity. They're really two different characteristics, and nobody knows up to this day why nature has chosen to have those two numbers be represented by the same number. Yes?
Could it be that they're actually different numbers and we just need
Yes.
more accurate measurements?
Absolutely, yes. And people do these measurements all the time. They were started, I think, by Cavendish. He certainly did a whole slew of measurements on these things a couple of centuries ago. And as far as we know, there really is no difference. that we have done using binary neutron stars, where indeed you still find that this is still upheld. I forget what the accuracy is, it's 10 to the power minus 6, 7, 8 or something like that. I mean, as far as we can tell, it really is the same number. But in principle, you could be right, that these things are really not the same number, only by approximation. But as far as we can test, same number. So this is one way of stating the equivalence principle. And let's be a little bit more puristic, we would call this the weak equivalence principle. Weak because it only applies, it's only stated about masses at this point. And later on we will see something that's called the strong equivalence principle, which is a statement not just on masses, mechanics, pushing and pulling, but all of physics. Okay? Now, this, let's call this a measurable fact, an experimental fact, comes with a huge consequence. Now, first of all, right, we've all seen these demonstrations before. You drop two things, and they fall at the same rate. You also seen this before, yeah? Okay. Just checking. Doesn't work. You know what the issue was. Air friction. So let's take the air friction away. There's still air friction, but I'm just making sure that the surface of these two things are both very small, so air has less surface to push against. Now, you know what, let's make things a little bit more definitive. No, I'm not actually. Either this or my
All you had to say,
Sorry?
are you sure?
It's being recorded, yeah.
Maybe a eraser on the whiteboard.
Just dump on the table.
Let's use it. Feel free to do this at home with your own chairs, okay? Now, masses are different. This is 100 grams or so, probably less. This is 4 times more, I think, something like that. Oh. Okay, so Liz is doing a bachelor project with me. So she and I are going to have a very stern talk later, okay? On gravity, I might add. Okay, so same amount of air friction, different masses, factor 4 difference or so. There you go, drop at the same rate. Now, this is of course just a restatement of this particular measurement fact, namely that the way either of these objects will drop is given by this formula, right? How it accelerates through space on its way down is given by Newton's second law. You just have to supply it with a force. Which force is that? Well, in this case, it's the gravitational force. The fact that this number is equal to that number means they drop out on both sides. If this were not the case, if nature had decided that these two characteristics of massive bodies are given by different numbers, they would have dropped at different rates. They don't. This is a way that you could test this. Just drop different things. Do extremely careful measurements and check whether they drop at the same rate. At the moment you find a difference, that apparently these two numbers do not agree with each other. So this, in a nutshell, is how you would test this principle.
But what is dropping them not produce the initial mass?
The dropping tells you how much it is being pulled towards Earth by this formula, right?
But which mass does that refer to?
This is the gravitational mass. How much is being pulled towards Earth? This is, given that's being pulled, how much does it accelerate? That's the inertial mass. And they drop out. So that means whatever you will get out, if you combine these two formulas, you will get some A, in this case it's going to be gm over r squared, where all presence of the thing that is dropping has dropped out. That's actually pretty coincidental, that one, but there is one in there. Okay? The mass of the thing that's falling has dropped out. So that means that apparently whatever you drop will have the same acceleration. In fact, if you put these numbers in, you put the mass of the Earth in 10 to the power 24 kilos. If you put r in, the distance from my little slippers of paper to the center of the Earth, which is about 6,400 kilometers, and you calculate what the number is. This is Newton's constant, 6.7 times 10 to the minus 11. You will get your 9.8, or your 10. Okay? Meters per second squared. So this is where that number comes from, which really is a strange phenomenon. It really just means that if you lift something up, you feel the difference, but once you let them go, gravity will make them fall in exactly the same way. Note my words. I have a phenomenon here in physics that will give the same acceleration regardless what the mass is of the object. Does that sound familiar? Just step to the side now, so clear view of the board, okay?
Something other than gravity.
No, fictitious forces. In fact, here, Newton's universal gravity is a force that is proportional to mass, and as a result, everything will drop at the same acceleration, just like a fictitious force does. So here's another statement of the equivalence principle. We're now at our third now, yes? The first one is these masses are the same. The second one will be equivalence principle, weak equivalence principle. Everything in gravity has the same acceleration. And here's a third statement. Gravity is indistinguishable from fictitious force. It has exactly the same properties. So again, I told you there's many ways to build up the equivalence principle. They'll ultimately boil down to the same thing. All masses under only gravity. You already saw that if you have air friction, then things do change. But if you leave all other forces out, you only leave gravity in, all masses have the same acceleration. So, we have a red block and we have a blue block. And one statement of the equivalence principle is, this is Einstein's, he says, gravity is as a phenomenon in physics completely indistinguishable from a fictitious force. Instead of saying something drops due to gravity, you could also say, you know what, it is as if I'm viewing the dropping thing from a non-inertial system and I'm watching its fictitious force. There's no fundamental difference in between the two things. This is what's called the equivalence principle. The two effects are equivalent to each other. Yes?
Is it a fictitious force in a specific non-inertial frame, or is it a fictitious force in all non-inertial frames?
In inertial frame. So for every time that you see something drop due to gravity, you can find a non-inertial frame of which its fictitious force mimics exactly that force of gravity.
So an arbitrary non-inertial frame.
A specific one. For a particular amount of gravitational force, you can find an inertial frame, a non-inertial frame, in which its fictitious force is exactly that gravitational force. So what the statement is not, you can go to any non-inertial frame and you will find that amount of gravity. In any non-inertial frame, you find an amount of gravity. So if you want to find one particular one, right, go to one particular inertial frame. So this here almost brings us to the conclusion that apparently gravity can be described as a fictitious force. Okay? That's our statement of the equivalence principle. Now, that comes with a very big conclusion. This already is a very big conclusion. But it comes with a direct follow-up statement. Let's see if you can parse this and see why. Therefore, gravity can be described by a curved spacetime. See if you can parse that based on what's written here. This, color-wise, symmetry-wise, we should be read on here. Same thing. Therefore, gravity can be described as a curved spacetime. That's a difficult step, isn't it? Who dares? It's curved. How about this? It is very, very close. Simon,
I'm thinking about the ball example,
okay,
where the ball follows a curved path. fall down instead of a straight path
Ah,
because there is.
Okay, that's actually very nice. I think this is also what you were saying. That this thing, as seen from the red coordinate frame, would follow something like this, right? This path or something like that, right? And if I would replace this ball by a completely different object, could be charged, could be much more massive, could be a little water, could be a chair. What path will it follow? The same one, right? That's exactly this this statement here. Okay. It is indeed as if it's just rolling on some curved object. Does the curvature depend on the mass? No, that's exactly the
Only
same.
the acceleration.
Only on the acceleration, if you will. Now, if I were to have, sorry?
Doesn't it also depend on the mass that's causing the gravitational acceleration?
That I agree with. That I agree with. So what you're now saying is, if you have a curved space-time, it itself must be made by a mass. That is true. Let's take that mass as given. Let's only focus on how, given a mass, some other mass will move. We see here exactly that any of these masses will follow the exact same path. It was this huge big conclusion here, yes? Okay. Now, if I were to envision in my mind that maybe there was some curved object here on which this thing had to roll, do you see that it really doesn't matter what the object is that is rolling down this particular curved thing? Because all of them would just follow exactly the surface of this curved thing. Okay? So therefore, the fact that everything follows the same curved thing, or looks as if it follows the same curved thing, is another way of saying, apparently, that gravity can be described by a curved thing. Right?
Are you meaning that you could actually draw a circle that would fit the acceleration?
Yeah, you should. Well, yes and no. What I'm now doing is that I'm just for didactical purposes drawing this curved thing in this particular case. Okay. It's not that there's actually a circle here. There's a formula, that's Einstein's famous field equations, that tells you how exactly this curvature will look, and it will probably not look exactly like the sphere that I'm drawing here now. So I'm only drawing this particular shape as a didactical example. The actual shape of the curved thing, that depends on all kinds of circumstances that we will see in the next couple of weeks. But the fact that everything falls the same way means that you can pretend, if you will, that things are moving on something that is curved. It's the curvature that determines how things move, not the object's own properties. So all of this just tells you this thing. This is the step that Einstein made. He said, okay, that apparently gravity can be described as if things, masses, are moving on something that itself is curved. So we've really made a huge step now. So let's recap everything, right? We told you it's going to be very light on the math today, but heavy on the concepts. What we've now seen is, in Newtonian physics, you go to a non-inertial frame, not a trivial exercise to get there, but suppose you find a non-inertial frame, you find everything falls in the same way. Just like things do in gravity. Therefore, going to a non-inertial frame is the same thing as introducing gravity. How do you introduce gravity? By looking at a curved space-time. Why do I say curved space-time, by the way? I mean, this is only space. Where does the time come from?
Well, right there in Newtonian reason.
Well, in our case, but in Newtonian physics, well, there is time in Newtonian physics, but it's not part of the curvature, right? But you already knew that in special relativity, you cannot have any space distances without time differences, durations, right? They're connected to each other by the Minkowski line element. So, if I say things move as if they move on a curved space, then automatically, in order to extend special relativity, to make sure that special relativity is still within the new theory, you also have to introduce time. Now, that answers the question that we started out with today. What happens in general relativity when you go to a non-inertial frame? You introduce gravity automatically. If you decide to describe things, you yourself, not from an inertial frame, from a non-inertial frame, you see fictitious forces, they feel like gravity for you, and you should describe them with the curved space-time. Any questions?
is the universe, like the known universe or the complete universe, if there's such a thing, is that considered an inertial frame?
Yeah, that's a little hard to say because the universe comes with a intrinsic curvature. As it does have a particular certain curvature that we will discuss in our very last lecture when we're going to apply all of this to the universe. So that very quickly answers the question. The answer is no. Because in order for it to be an inertial frame, that means you should be in a space-time where there is no curvature. And that is simply not the case. Now, at the same time, of all the possible curvatures that the universe can have based on what we see on our measurements, there's only three options. And one of them looks like a flat space-time. So it is like an inertial frame. So, okay, we will see this in our final lecture of the series. But based on our understanding of the universe can only have three curvatures: spherical, hyperbolic, and what we call flat. The measurements have to tell which of the three is actually the one. And it turns out it's the flat one. In that sense, it is like as if the universe is a non-curved space-time, but here's a twist. It is space-time, a flat space-time, that itself is extending. So it does not have curvature in the sense that things move in a curved way. It is still flat, like a sheet, but the sheet is accelerating. And then it becomes a matter of semantics whether you still want to call it a curved or non-curved space-time. So it has all the geometrical properties of a flat space-time, but it is a flat space-time that itself is expanding in size.
Okay, but you would say that like the net curve, so to say, would be zero. Right? I'm not sure I'm using the right terms for this.
It depends on how exactly you are going to define curvature. So let me give you a quick definition of curvature, okay? One possible definition. One possible definition of curvature is that if you have two lines that start parallel, they keep on being parallel. That would not be the case on an actual curve. On a curved space-time, like a globe or something like that, two parallel lines at some point will find each other. So one way to measure whether a particular space-time is curved is by drawing two lines and see whether they get closer or further away from each other. In that sense, the universe is flat. Because two parallel lines will never start moving towards each other or creep away from each other. So in that sense,
except in gravitational.
Yes. What is the case is that the other side of the universe is moving itself away. So the straight lines stay parallel, but they do stretch out. But they do stay parallel. So if your definition is do straight lines stay parallel, then the answer is yes, the universe is a flat space-time. There's actually a name for this. It's called a flat Friedmann-Robertson-Walker space-time. Again, the final lecture of the series. Any more questions on this? Okay, so what we'll do in the tutorial, we're going to look at some curved spacetimes. We're going to see how you can mathematically describe this. I will tell you how this is done. And then from next week onwards, we will apply this to general relativity for actual cases. Okay, thank you, people.
You have the lecture.